Hey everyone, if you're following along with the rate of dissolution and solubility note guide at home, you recognize that we have a problem. Our aunt has called. I'm not sure how insects have phones, but she's called nonetheless, and she's arriving for a surprise visit in 20 minutes. We need to make some sweetened iced tea, so what are we going to do? Well, speed is an issue, and so it turns out that different things affect the rate of dissolution, aka the rate at which things can be dissolved. And so we know that maybe temperature has a role in this. If you'd like to pause the video and think about what else you might be able to do to make this happen, you can do that. But if you pause the video, let's move forward and talk about these factors. So we're going to talk about that temperature factor, but it turns out that stirring also increases the speed of dissolving as well as surface area. So surface area, what do we mean? If we could take, let's say, a cube of sugar and put it into a mixture that looks like this, it's going to take a lot of time for all of these water molecules to collide with that cube of sugar and gradually break off the little piece of sugar. This picture is actually of table salt, but let's pretend it's sugar. And it's going to take a while for all of those individual sugar molecules to break up. But what if we put in powdered sugar? If we put in powdered sugar, then there's way more surface area for these collisions to occur, and therefore it happens quicker because we've already broken down the solute a little bit ourselves, and so we've created more surface area for collisions to occur, and that allows the dissolving to happen faster. We could also stir, right? Because as we stir, we're not only going to increase potentially a little bit the speed of collisions of these water molecules with the solute molecule, but additionally, we're going to keep mixing up these areas of high and low concentration, and we are going to be able to spread out the solute and make it accessible to more collisions with those solvent molecules. So that's going to also increase our rate. Temperature, also we know about, and the reason that it increases the rate at which we're able to dissolve stuff is based on kinetic energy, right? So if we have these collisions, and those collisions are a little bit stronger, if you have strong collisions, the more effective they are at breaking apart a solute, and the better you break apart the solute, the quicker you have it able to be dissolved. So we're going to do things a little bit out of order here. Jump down to the bottom of your note guide. We're going to do one practice problem at this stage of the game. Let's think about why we might expect a packet of sugar to dissolve faster in hot tea than in iced tea. And like we just talked about, if we increase temperature, we increase the kinetic energy, we have more effective collisions. If we have faster and more frequent and stronger collisions, then we break apart those solute molecules a little bit more quickly. So that's your first practice problem. Let's jump back in up on the note guide. We're going to talk a little bit more here. And let's think more about our iced tea and our sugar. So gradually, if we're adding sugar into the iced tea and we want to dissolve it because our aunt wants that sweetened iced tea, we're going to be able to dissolve a lot of sugar, but eventually there has to be a place where we can't put any more sugar in, right? If we tried to put 5 pounds of sugar into a cup of water, it's just going to dry out that water, right? There's got to be a limit to how much we can put in. So that limit we refer to as the solubility. And so we're going to have different concentrations of solutions that we're going to discuss in this video. But before we get there, let's talk about the equilibrium that occurs, and we've alluded to this briefly. So it turns out as we have this particle over here, maybe it's sugar, this one looks a lot more like NaCl, as it's being dissolved, as we have collisions breaking off part of this solute, they're all breaking off, and these purple ones, let's say those are the ones that are dissolving. It turns out that some of these green ones, they are recrystallizing. They're forming back on the crystal because the crystal has these charges, right? So there are partial positive, partial negative charges. So there are places where it wants to kind of stick back together like a magnet. And it turns out the rate, whenever that process equals out, the rate that is becoming recrystallized, forming back to the compound, and the rate that is dissolving, going into the solvent, essentially, when that's equal, we have reached equilibrium. So ultimately, we call that solution equilibrium. It has a definition. It's the state at which that process of dissolution and the recrystallization of the solute, whenever those things are happening at an equal rate. Okay, so whenever we make our solutions, it turns out we have some more terminology, and we think about whether things are saturated or unsaturated. So saturated is a word that means full. If something is saturated, it's completely filled up. You may have heard of like a sponge being saturated. A sponge that is saturated is probably dripping wet. It can't hold any more water, so the excess water is falling off. Whereas something that is unsaturated, if you're unsaturated, you can still hold more. And so if you think about it, there are many, many different unsaturated solutions, right? So you could have a really, really unsaturated solution that can hold way more solute. You could have a kind of unsaturated solution because it's holding some, but it could hold more. But as long as you can hold more solute in that solution, you are unsaturated. So here's a good graphical representation of that. So here we have some compounds being dissolved in water. And so this is sodium acetate being dissolved in water. And you'll notice it's at a constant temperature, so we don't have to worry about temperature changing. We have a constant amount or volume, in this case a mass actually, we have a constant mass of water. And as we start to add, this is a mass down here on the x-axis, as we start to add grams of this solute into the water, you'll notice we can dissolve more and more. So this red line going up is the amount that we're able to dissolve, but eventually we hit a point where we can't dissolve anymore. So that's when we say this solution is saturated. We are completely filled up with the solute that we're trying to add. And if we're completely filled up, it can't hold any more, that is saturated. But you'll notice from this point to the left, these are all unsaturated. So there are many unsaturated solutions because all of these are able to hold a bit more. And where this thing levels off, where we end up with no more solute being able to be added, that is our solubility. So we say that the solubility of sodium acetate in water at 20 degrees Celsius is 46.4 grams per 100 grams of water, because at that point we can't hold any more and our line levels off. What if we could hold more though? So we talked a little bit earlier about the ability of, or the characteristic that temperature allows us to increase our solubility of a solute in a solution or in a solvent. And so if we increase the temperature on the previous graph, if we increase the temperature, let me go back there for a second, then our solubility is also going to increase. It's going to go up. And so what if we increase the temperature and then we allow it to slowly come back down to equilibrium? Let's take a look at a video here of what's going on. So we'll just let our video load. And let's see a supersaturated solution in action. And hopefully he'll load quickly. We're having internet problems, but he's going to drop a crystal into this solution, and notice what happens. All of a sudden, you're seeing a ton of crystals forming across his solution. The solution in this beaker is a supersaturated solution. How do we know it's supersaturated? Because look at all those crystals just growing out of the one that he's dropped into the beaker. So we may do this ourselves in class, but I figured I'd give you a little representation of it here. So all of those crystals are forming because they're coming out of solution rapidly. And this happened because he made a supersaturated solution. So let's come back to our slides here. So why did that happen? Well, what he did is he took some solute and he increased the temperature. So he dissolved way more in a given amount of liquid than he should have been able to. And then as he let it cool down, it turned out that the crystals didn't come out of solution. They were kind of stuck there until he basically upset the situation. And he upset it by adding a crystal, and that crystal caused many, many other ones to form. So here again, our supersaturated solutions kind of explained. You'll notice as the temperature decreased, we're still able to hold more solute than we expect. And then as soon as he added that crystal, or if we kind of jostle the solution, all of those crystals are going to come out at once. So let's finally talk about a little bit of numerical values. So the solubility of something is basically the ability of it to be dissolved, and we can measure it in terms of the amount of solute that is dissolved in order to form a saturated solution. As we saw with supersaturated solutions, we need to use a very specific temperature, because if we change the temperature, we change the amount that can be dissolved. So here's a graph of different temperature versus solubility relationships. So on the x-axis down here, we have the temperature, and you'll notice as you increase the temperature, in general, the solubility increases. These are getting a little bit steeper. So first off, notice that depending on what you're dealing with, the amount of solute that you can dissolve changes. So if we look at something like sodium chloride in water at 0 degrees Celsius has a solubility around 35 grams per 100 grams of water. And if we get it all the way up to 100 degrees Celsius, it goes up to about 40. So there's only a difference of about 5 grams of NaCl that we can dissolve if we increase the temperature of the water a full 100 degrees Celsius. That's very different than if we look at something like sodium acetate. Sodium acetate also has a solubility of about 35 in 0 degree water, but if we increase the water of that to 100 degrees Celsius, it goes up to 170 grams. So we have a 135 gram difference. So this was a 135 gram difference. This was a 5 gram difference, right? Massive, massive difference. So different compounds are more dependent on temperature. There's another weird thing going on here while we're on this graph. Check out SO2. SO2 has the reverse relationship going on. It looks like as we increase temperature, the solubility decreases. And so think for a second what might be causing that. And if you remember back to our previous video, it turns out that gases, if you increase temperature, the solubility decreases. So this must be a gas. That's sulfur dioxide being dissolved in water. Here are some other data that basically shows you solubility in water. And so I'm showing you this just so that you're aware that we could give you data like this. It's showing solubility of different solutes as you go down this part of the table in different temperatures of water. And notice the amount of water is always constant, 100 grams, but this shows you the different solubilities, so we can see it in graphical form, we can see it in table form, but we're seeing very much the same thing. Let's try one more practice problems. Let's explain how we might prepare a saturated solution of sugar in water. Well, you could look up the solubility of sugar in a certain temperature of water and then add that much. Or you could basically keep adding sugar until some of the sugar forms at the bottom, and as soon as some of the sugar forms at the bottom of your beaker, you know that the resulting solution up here is saturated because some of that sugar is falling out of solution. So therefore you have a completely saturated solution. What if we then wanted to take it a step further and we wanted to make it supersaturated? Well, if we wanted to do that, we'd have to increase the temperature so that we could dissolve more and more sugar. And then we would gradually let this thing cool back down very slowly. And as it did, we'd be holding more solute than we once thought possible, which is our definition of supersaturated.